Hey guys, welcome to our lesson on aromaticity. Aromaticity is really important for many biological molecules, like DNA, for example. So we're going to go over the concept of it, as well as some examples of what an aromatic molecule can look like and how to predict aromaticity. So what is aromaticity? So we're actually going to start by looking at cyclohexene and benzene and kind of comparing their heats of enthalpy. So here kind of what I'm showing here is this reaction. It's called catalytic hydrogenation. So what it means is that, in case you're wondering, you don't need to know this too much detail, but basically we're getting rid of this double bond over here. So you guys basically result in, now you have these two hydrogens instead of just that one coming out. So this is something you'll learn more about in the next level of organic chemistry. But for our purposes today, we don't need to really know the mechanism. But just so you know, the reaction itself releases about 120 kJs per mole. And looking at benzene, you would imagine that, since it has triple the amount of pi bonds, as opposed to cyclohexene, you would think that its expected delta H would be 3 times this amount. So you think it'd be maybe around 360 kJs per mole. But in actuality, benzene is extremely stable, like way more stable than you would expect it to be. And its delta H is actually about only 208 kJs per mole. And this negative basically means that it's exothermic. And these delta H's kind of indicate the stability of these double bonds here and the stability of these molecules. And so when you have a smaller numerical value for this delta H, this actually indicates a more stable double bond. And so when you look at benzene, you find that it's extremely stable. And this is because it has this characteristic of aromaticity, which basically means that you have a very, very stable molecule that's brought about by a certain number of pi electrons, a certain number of p orbitals, and we're going to go a little bit more into detail about that on the next slide. So in order to have aromaticity, which is basically a very special stability, you need a closed loop of adjacent, parallel, and overlapping p orbitals. So again, you have this requirement of the p orbitals. You do need to have planarity, so you want a flat type of molecule, and you also have to obey Huckel's rule. And Huckel's rule is this equation for n plus 2 to represent the number of pi electrons that the molecule should have. And it must satisfy this rule in order to correctly be aromatic. And so let's take a look at benzene over here. Again, we know that it's aromatic because it has a closed loop of p orbitals. You have your p orbitals over here are making these pi bonds. So there's this closed loop, as you can see. It's very planar, it's a flat molecule. And then the Huckel's rule is basically we want to see, first of all, how many pi electrons does it have? So basically, how many electrons are hanging out in the p orbitals? So we have 2, 4, 6 pi electrons here in benzene. So basically, the number of pi electrons has to satisfy this rule. And your n needs to be an integer. So in this case, we have 6 pi electrons. 4n plus 2 is equal to 6. N is therefore going to be equal to 1, which is an integer. And thus, benzene satisfies Huckel's rule, and it is therefore aromatic. So just to summarize what I just did there, I counted the number of pi electrons. I counted the number of lone pair electrons in p orbitals, but in this case, there were no lone pairs in benzene. And then I asked myself, does it equal 4n plus 2 where n is an integer? So those are the 3 things that you should keep in mind when trying to test Huckel's rule. So let's look at this molecule here. I'm going to start first by drawing in these lone pairs here because we definitely want to make sure that we don't forget these. And these lone pairs of the nitrogen are also hanging out in some p orbitals. So we have 2, 4, 6 pi electrons. And again, we want to make sure that that satisfies Huckel's rule. Huckel's rule, again, n is equal to 1. So this is aromatic as it also is planar and has a closed loop of adjacent p orbitals. And you can see that here, this closed loop right here. Okay, so, and just to clarify, building off of a previous video on conjugation, every aromatic molecule is conjugated, but not every conjugated molecule is aromatic. And the reason for this is every aromatic molecule does have that adjacent overlapping parallel p orbitals. And in fact, for conjugation, you need 3 of these. And in aromaticity, you do have 3 of these, but they're in a loop. And in aromaticity, similarly, you can't necessarily have a conjugated molecule that's always aromatic because it might not always form that closed loop. So just kind of a connection here about how we're relating the two concepts. So let's look at some examples of aromatic molecules and determine whether or not they're aromatic. So here we're going to first look for some things that are important. These are the 3 requirements we need to have. So let's see. Does this have a closed loop of adjacent p orbitals? Let's go through and circle all of them. Looks like there's p orbitals here. That is indeed a closed loop, so we do have that. Is it planar? It's a very flat molecule, these 3 fused benzene rings. We know benzene is planar. Does it satisfy Huckel's rule? So again, the 4n+2 rule. So let's see. We have 2 pi electrons here, 4, 6, 8, 10, 12, 14. So let's see, we have these 14 pi electrons. So let's see, you're going to do some basic algebra here, and your n is equal to 3, which is an integer, and so it does in fact satisfy Huckel's rule, and therefore it is aromatic. Let's test out this molecule now. So we have a methylpyridine here, and we're going to look for, again, that closed loop of p orbitals. We do indeed have that. And we have a p orbital actually here where these lone pair electrons are. Don't forget the lone pair electrons. So we do have that. We do have planarity, has similar kind of structure to benzene here, and Huckel's rule. So let's be careful here when we're counting our pi electrons. So we have again 2 here, 4, and then let's look over here. So we know that there's a lone pair of electrons on this nitrogen right here. And we have, that p orbital here with these pi electrons. And these pi electrons, these lone pair electrons, are hanging out in these p orbitals. So when you're counting this, since these lone pairs are already in the p orbital, you don't want to double count it, basically. You don't want to count this and have like 2 and 4. You don't want that. So what you should do is kind of, keep in mind what the molecular structure looks like and what the p orbitals look like. So what we really have here is 2, 4, 6 pi electrons. This is that bond between them. So we have 6 pi electrons. And as we remember from experience, n is going to be equal to 1. And therefore it does satisfy Huckel's rule. So it is aromatic as it meets 3 requirements. Lastly, let's look at this molecule. This is 10-annulene. Again, we're going to look for that closed loop of p orbitals. Looks like we have that here. Indeed. And then we're going to look for, I'm actually going to skip over this one and look at Huckel's rule first. So 2, 4, 6, 8, 10. So your n is going to be equal to 2, so it does satisfy Huckel's rule. Then we're going to look at planarity here, so let's be careful because if you imagine what the 3D structure of this molecule might look like, and it's good to have your some kind of model kit to kind of view this, but these hydrogens are actually going to be coming in and kind of trying to occupy the same space. And so this is, if we were to make this a planar molecule, it's very unlikely. There's a lot of strain, there's a lot of ring strain, there's a lot of, it's too unstable here for these hydrogens to occupy the same space because of this type of trans alkene structure that we have going. And so, as a result, this molecule actually is not planar. It kind of, if you have a model kit, you can see how it kind of pushes these hydrogens so that they don't occupy the same space, and as a result of that, it breaks the planarity. So this actually does not satisfy the planarity rule. So this is actually an exception. I just wanted to put this example here so that you can remember you shouldn't always just automatically assume that a molecule is planar. Always just kind of take a look at it, imagine. It's good to have that model kit and see what it looks like. So unfortunately, this one is not aromatic either. And that's kind of all you need to know for aromaticity. Thanks, guys.